Myself Himanshu Panadiwal, working as an assistant professor in School of Engineering at Avantika University, Ujjain. Today I am representing one of the core technical subject, theory of computation, and I am presenting different topics related to computation and also related to compiler design. Okay, so before the further delay, we can start our presentation on theory of computation. Okay, so these titles basically belongs to the computation, and here we discuss about the machine languages, different types of regular languages, regular expressions, DFA, NFA, and differences between deterministic finite automata, non-deterministic finite automata, and some of the closer properties of regular languages and Chomsky classification of grammar. Okay, so here in today's lecture we cover first the introduction part, and next is Chomsky classification of grammar. Okay, so according to Chomsky, grammar is divided into 4 parts. Accordingly, type 0, type 1, type 2 and type 3. Second is the basic relationship between languages and machine, and regular expression, DFA, NFA, design, how to design DFA and NFA, and design of finite automata from regular expression, any, and closer properties of regular languages. Okay. So, the theory of computation is the subject that deals with language processes, how languages processes and which language is correspond to or related to which grammar. Basically, like in English language, in theory of computation, languages and grammars, the combinations of languages and grammars. Okay, so here are in grammars some set of rules are there basically. So languages is a set of string or set of sentences, and grammar a set of rules. With the help of grammar we can generate the language. So basically grammar G is divided into 4 tuples. VTPS is defined, V for variables or non-terminals, T for terminals, P is the production rule, and S is the starting symbol. So here the example of our grammar, S tends to A, B. That is represent, S is capital letters represent the starting symbol. S tends to AB, so AB is also a part of non-terminal. And next production rule is, there are 3 production rules. Production rule 1, production rule 2 and production rule 3. So 3 non-terminals are there, S, A and B. S belongs to starting symbol, A belongs to another non-terminals and B belongs to another non-terminals. And small a and small b are the part of terminal. So basically it is also known as the production rule of the grammar. Terminals are the parts of string. The overall non-terminal helps to generate the string. S is a starting symbol or a special non-terminal which represent the starting symbol of a grammar. So language generated by previous grammar are the combination of VTPS. We already discussed about the VTPS. So VT in the parts of variable or non-terminals, that is A, S, A and B. T is a terminal, and terminals are belongs to A and B. S is a starting symbol, and these are the 3 production rules. The intermediate states, how to define the complete string form. So there are some intermediate states. So intermediate state is called sentential form. Like S tends to AB. So first A and capital A replaced with small a. So the production rule is obtain AB. Now in the second step, S tends to AB. So B, capital B replaced with capital AB. Now the second A converted into small a, and overall the sentential form is double AB. The third stage is AB, then now convert capital B into small b. So overall the given grammar converted into string, so we obtain the result double A double B. So that language generated by a grammar. So we already discussed about the theory of computation basically belongs to the languages and sentences. Okay. Then the first language is to obtain a particular grammar, that is A tends to n and b to the power m. A to the power n and b to the power m, and particular nm belongs to 0. Nm greater than equal to 0. So any number of a's is followed by any number of b's. Here the grammar is A tends to a to the power n and b to the power m. So here the number of a's and number of b's. Number of a's is followed by any number of b's. Here showing the this particular language. And another form is the essential condition is at least one a and one b must be present. Taking another example, that is example number 2. So S tends to A S B, and here the special non-terminal lambda we consider it. Lambda is a special terminal. So define the language after generated the string. So the language is a part of grammar. So we obtain a language lambda. Another string is AB. If put the value lambda in the given starting symbol, that is ASB. So we obtain as the result AB. Second is the second position S, that is the number of times AB, AA, BB, and 3 times AA, BB up to so on A to the power n and B to the power n. So we obtain the language in a particular grammar is A to the power n and B to the power n, and the condition is n greater than 0. So here we represent or we conclude that the particular grammar resulting equals number of A's and B's. Okay. Then according to Chomsky, grammar is classified into 4 parts. Type 0 or unrestricted grammar, type 1 context sensitive grammar, type 2 context free grammar, or type 3 or regular grammar. So depending on the production rules, Chomsky classified the grammar into 4 categories. So these are the production rules defined by the Chomsky. That is the first rule, type 0. Type 0 grammar is also called as unrestricted grammar. There is no restriction from left hand side or right hand side. Here representing the production rules. So in production rules, we define alpha tends to beta. So here are some conditions from lambda, alpha to beta. So condition is alpha, beta are the set of terminals and non-terminals. That is variables. Basically non-terminals are called a variables. So V union T the whole star. So there is no restriction on lambda, alpha and beta. Here the example of type 0 or unrestricted grammar is E small a and capital A tends to capital B and small b. Second is capital A, small a, capital A tends to small b. So there is no production rule. See the example on the left hand side or on the right hand side. There is no set of rules is defined. There is also called as unrestricted grammar. So we move forward. The next grammar is type 1 grammar. So type 1 grammar is also known as context sensitive grammar. So see the production rule of context sensitive grammar is alpha tends to beta. Here are some conditions in that case of context sensitive grammar. Length of alpha and beta. Okay. So define the length. The length of alpha should be less than equal to length of beta. Again, the alpha and beta are belongs to the V union T whole power star. So alpha, beta are the set of terminals and non-terminals are variables. So left hand side should contain at least one non-terminal. The essential condition of context-sensitive grammar. Left-hand side contain at least one non-terminals. Here see the example. In taking example 1, small a and capital A tends to capital B and small b. This is allowed in a context-sensitive grammar. But move to the forward second example, small a, capital A tends to B. That is not allowed in context-sensitive grammar. Third production rule is called, according to Chomsky, type 2 or context-free grammar. So context-free grammar also used in compiler design, that is compiler design phases. So basically in compiler design, that is divided into 6 phases. So phase number 1, that is lexical analysis, and phase number 2, syntax analysis. So in syntax analysis, we are using context-free grammar for generating a particular grammar or generating a production. So in context-free grammar, the production rule is of the type alpha tends to beta. The left-hand side or alpha must be a single non-terminal only. The essential condition is. And beta are the set of terminals or non-terminals, that is variables. So here the example of context-free grammar or type 2 grammar is A tends to capital A, small a, capital B. This is allowed. This is the valid example. Taking another example, A tends to capital A, small a tends to B. So this is the incorrect way. So not allowed in context-free grammar. Third type of, according to Chomsky, that is regular grammar, type 3 grammar. So in this production rule, alpha tends to beta, where alpha equal to single non-terminal. The same condition as the context-free grammar. And beta is a terminal, or first condition in particular beta, a terminal or a terminal followed by a non-terminal. The second condition same as a terminal or non-terminal followed by a terminal. The right hand side should of the form in these 3 rules. Either the single non-terminals, second single non-terminals, terminals followed by a non-terminals, or non-terminals followed by a terminal. Okay. So see the third example. These are the 2 valid cases. A tends to small a, also valid, because on right hand side is single non-terminal, single terminal. And in third case, there are two terminals. So it's violating the rules of type 3 grammar. So this is a invalid production rule. Now, after the discussion of Chomsky classification of grammar, type 0, type 1, type 2 and type 3, we move forward the properties of Chomsky classification of grammar. So we conclude that type 3, according to computational power, type 3 is a subset of type 2, type 2 is a subset of type 1, and type 1 is a subset of type 0. So according to computational power, type 0 is most powerful language. So different types of language with their grammar. So regular language is a part of type 3 grammar. Context-free language, type 2 grammar. Context-sensitive language, type 1 grammar. Here the variation in unrestricted grammar or type 0 grammar, because unrestricted language further divided into 2 parts: recursive language and recursively enumerable language. Now see the relationship between languages and machine. So see the diagram belongs to the type 0, type 1, type 2 and type 3. So here the first language is type 3 language, that is less powerful regular language, and its acceptance model is finite automata. The second one is, move forward, the second one is context-free language, and its acceptance model is push-down automata, that is more powerful than regular languages. The third one is context-sensitive languages and its acceptance model is linear bounded automata. And fourth one is unrestricted language and most powerful acceptance model is Turing machine. And unrestricted language further divided into recursive language and recursively enumerable language. So arrangement of machine according to decreasing order of their power. The most powerful machine is Turing machine. And linear bounded automata is the next, and accepted language is context-free language. Next is push down automata, and acceptance language is context-free language and is less powerful. So the relationship between languages and machine, the most powerful to least powerful languages, Turing machine, one of the most powerful acceptance model or machine, and less powerful is DFA. Now move forward. Automata theory. The regular expression is defined by the representation of regular grammar or regular languages. So to define the regular languages and regular grammar in a particular form, we are using regular expression. So regular expression defined as something like that, a to the power star. So basically in theory of computation, stars representing the power in the form of 0, 1, 2, 3 and so on. So the language is where star 1, 0 up to infinite defined star. And next is A plus. So A plus is defined, power starts with the 1 to infinite. Another interesting part of theory of computation, that is phi. In theory of computation, phi is a regular expression which represent empty set or null set. Here the representation of phi is empty set. So in curly braces nothing is given, that is represent the phi. And another regular expression is A plus B or A union B equal to A B in a particular set, or either A or B. So both things are same. Second one, if we multiply the 2A plus B. So see the result in a particular language set, AA, double A, because first A multiply with first A, second A, first A again multiply with second B. Now first B multiply with the second A and first B multiply with the second B. So see the overall result, double A, AB, BA and BB in the form of string. So another example of regular expression, A plus B whole star. So A plus B whole star basically accept all the languages, all the numbers from 0 to infinite. The difference between A star and A plus is that A star accept the numbers from 0 to infinite and A plus accept the number 1 to infinite. So A plus B whole star said the language obtained as L equal to lambda AB small a single b AB double B any combination of AB. Means there is no restriction between either A comes first or B comes first. So representing all string of A and B. Second example of regular expression, A star B star. So this particular regular expression representing the combination of AB, single A, single B, A double B, double A, B. Means also lambda, it considered as a language with representing the any number of A's and B's, but A's comes first and B's comes second. So in every cases A's followed by B's. Now the equality, check the equality of regular expression. So taking another example, this is the example of regular expression A star B star equal to B star A star. But both are not equal because the combination of AB first sentence or first rules regular expression represent A's comes first, means A's followed by B's, and second is B's followed by A's. So both are not equal in that particular case. The second expression is A star B star whole star equal to B star A star whole star. The changes between the previous example of regular expression and the current example is that the whole power of star means it's accept the value of lambda. So overall it's conclude that A plus B whole star. So both are equal. Second example, we check the equality. After the equality, if the given language in any particular language is regular or not. So how to check it? So taking the first example, L1 equal to A to the power n is regular or not? The solution is just we are belongs to the A to the power n equal to A to the power star, because A to the power n accepting the value from 0, 1 up to infinite also is the similar as the A star. A star also accepting the value 0 to infinite. So both are equals, but counting is not possible from A star or an, but equivalent regular expression is possible. So in case both are equal, so we can say that the L1 equal to A to the power n is regular language. Second example, L2 equal to A to the power n, B to the power n. No regular expression is possible between them, and if it is possible to draw an finite automata for that language, then that language will be a regular. Okay. So another condition to check this particular language is regular or not, simply we just draw a finite automata. The following conditions for any regular expressions to be regular. Check these three conditions. A language is said to be regular if it is satisfy at least one property given below. Either three condition, we should satisfy at least one condition. If it is possible to write a regular expression for a language. Second, if it is generated by a regular grammar. If it is possible to design a finite automata FA for the language. Okay. So check any three conditions. We must satisfy the one condition. Then that particular language is called a regular language. Now move forward. Automata. So what is the meaning of automata? There are automata belongs to the automation. There are some machine automation or some kinds of production rules or some kinds of computation. We perform computation. So an automata contains a finite set of state. At each instance in the time of run, if machine is run, then the automation is one of its states. Means it's changed the states from one to another. Once the input words has been read, the automata is said to have been stopped, and the current state at which automation has stopped is called as final state. Means the automation is complete. Means all inputs are completed. So the final state, the overall final state is called a final state or the end state. The set of all the words accepted by an automata is called the language recognized by the automata. We already discussed previously the type 0, type 1, type 2 and type 3 grammars. So finite automata, overall the language acceptor which accepts regular languages. So see, notice that the point, finite automata is a language acceptor which accepts only the regular language. There are two types of finite automata. So regular language acceptance model is finite automata, and finite automata is of two types. First is deterministic finite automata, that is called DFA. Second is non-deterministic finite automata, also called as NFA, but in terms of computational power. So both are equivalent in power. Matlab both DFA and NFA produce the same computational power. See the definition of deterministic finite automata. So DFA is a set in which there exists one initial state and one or more than one final state. The basic setup or machine setup of deterministic finite automata. So a DFA is defined by 5 tuples. Here the machine or tuples representing Q summation, first is Q, second is summation, third delta, initial state defined by the Q0, F is the final state. So see the 5 tuples. So DFA is a combination of 5 tuples. Q is a finite set of internal states. Summation, finite set of input alphabet. Delta is a transition function where to perform a transition from between the states from Q0 state to Q1 state or Q1 state to QF state, that is final state. Q0 is the initial state, starting symbol with the oval symbol with the arrow. F is the final state and it is a subset of Q. Also F is a part of Q. Now the deterministic finite automata, for each input alphabet there is an exactly one transition at every state for every input in DFA. Each move of the DFA take only one input alphabet. Means the difference between DFA and NFA move forward. The basic difference between DFA and NFA, DFA just accepts only every input in every state. When the end of the string is reached, the string is accepted, otherwise the string is rejected. So the DFA whose initial state is final state, then it accepts lambda, that is null string. Also DFA accepts the null string, and there is also exists a state known as the trap state. Because some additional states are required, the transition is completed, which has self loop of all the alphabets. So there is no null transition in DFA. To see the example of DFA, so define the DFA, the basic structure of DFA. This is a Q0 is a initial state, a circle symbol with the arrow. Define the initial state. See the every transition either A or B. This is particular A self loop of AB, and Q2 is a final state. So final state representing the double circle. See the another state or additional state is called a trap state, because in DFA the condition is that the condition is given. Design a DFA for the language in which all strings starts with AA. So string starts with A over the alphabet set AB. So there are the condition A, the essential condition. So to make the DFA in the form of AA string. So first A, then second A. So states is completed. Now the additional transition of B, just put on the state that is called trap state, and in trap state another transition A and B. So see the complete structure of DFA. Taking another example, the language which contains any number of B's and exactly 2 A's means accepted any number of B's, but essential condition is exactly 2 A's. So start with the previous example again. The example is AA, and last one, the third A is belongs to the trap state, because our transition is completed AA. Third example of DFA which accept even number of A's and even number of B's. So Q0 is also a initial state and Q0 also a final state, because the transition A and its completed second transition, another is A. Again, the another example or another transition is A, B, A and B. So there is the count of even number of A's. So 2 A's and 2 B's. So any combination, we try to solve any combination in a particular question, the output is the same even number of A's and even number of B's. Third example, and interestingly, NA, W mod 3 means number of A. Basically, NAW belongs to number of A mod 3 not equal to 0. Means it's accepted the single A or double A, but the third A is not accepted. Then design a DFA for the language in which number of A's and number of B's are divisible by 3. So number of A's and number of B's is divisible by 3 means count of A and B's are in the divisible manner by 3. So see the first transition A, then second is again A, B, B, again A and B. So here the counts of number of A's is 1, 2 and 3, and counts of B is B, B and B. Okay. So in any combination of transition, the number of A's and B's are divisible by 3. So total number of states are there is 9. 1 initial states, and again initial state and final states are same. Now move forward, the another type of DFA, another type of finite automata, that is the next version is non-deterministic version. So non-deterministic version, that is called NFA. So NFA is a finite state machine where for each pair of state and input symbol there may be several possible next states. So there is no condition between A and B transitions are equal or its cover. Same as the DFA. The difference between there is the number of A's and number of B's are increasing manner. So this distinguishes it from the deterministic finite automation where the next possible state is uniquely determined. So it may be shown in the formal theory that are the equivalent in that for any given DFA, one may construct an equivalent DFA and vice versa. So definition of non-deterministic finite automata again defined by the 5 tuples. Tuples is the same as the DFA, Q summation delta Q0 and F, where Q is the set of internal state, summation is same as the set of input alphabet, delta is the transition function. So difference between in the DFA and NFA in the transition function. Here Q summation belongs to delta, that is 2 to the power Q. Q0 is the initial state and F is the final state, and it is a subset of Q. Now taking the example of non-deterministic finite automata. So see the first example. Design an NFA for the language in which any number of B's is followed by AB. Means any number of B's. So we define in DFA or NFA, any number of B is representing the self loop. So see the example, P is the self loop, means it's accepted any number of B's, and accept AB. So just the single transition from Q0 to Q1 A and Q1 to Q2 is B. There is no restriction to cover the transition A in Q1 or transition A and B in Q2. That is called NFA. Second example is NFA for the language that contains any number of A's and exactly 2 B's. Second condition is exactly 2 B's except any number of A's. So again, define the any number of A's in the case of self loop. So start with the state, initial state Q0. First A accept the any number of A's in the form of self loop, then B single B. Condition second, exactly 2 B's. So any number of A's and exactly 2 B's. Third example is NFA, design an NFA for at most 2 A's and any number of B's. So at most 2 A's means essential condition is 2 A's means it starts from the Q0 states, one transition for A first A and second A, then move to the final state. There is no condition to the B. So in that particular case, Q0 is also a final state, Q1 is a final state and Q2 also is a final state. So both Q0, Q1, Q2 are the final state in 2 A's and any number of B's condition of NFA. Now the basic difference or the essential difference after we moving forward, DFA and NFA differences. We see the basic properties of DFA and NFA, basic tuples of DFA and NFA, how to design DFA and NFA, and taking more examples of DFA and NFA. So all the properties of DFA, NFA are the same as of the DFA. But the major difference between DFA and NFA, for each input alphabet, there is exactly one transition at every state. While in NFA, where maybe one or more transition for each alphabet at any state. So NFA allows lambda transition for every state. NFA, there is a DFA which accepts the same language. So DFA and NFA are equivalent in computational power, means accept the same manner the inputs and outputs and computational power. We generate the result in the same way. So now we move forward the design FA for a particular finite automata from a regular expression. So see the first regular expression. We already discussed about this regular expression. A star B whole star means Q0 is the initial state and also it is a final state. And the whole soul transition is AB. AB is a cell loop. Design an FA for the regular expression. So A star and B star means any number of times A and any number of times B is accepted. So we define the A's and B's is just the Q0 self loop of Q0, and we move forward from Q0 to Q1, that is B. So self loop of A and self loop of B in both cases of Q0 and Q1, and Q0 and Q1 both are the final state. See, there are some properties of regular languages, some closure properties and non-closure properties are there. So we cover first the closure properties of regular expression. So see, the first property is the union, second is intersection. So union is L1 equal to, if suppose to the two languages are given, first is L1, that is A star B star, second L2 belongs to the B star A star, then simple perform its union. So what is the result from L1 union L2 is A star B star plus B star A star. So regular expression are closed under union because we are taking two examples, L1 and L2, and perform the union. So third one, generate the language A star B star plus B star A star, also a union. So the properties under the union is closed in the case of regular language. Second property is intersection, means perform same example A star B star and B star A star, perform the intersection to see the result A star plus B star. So regular expression A star B star also belongs to a regular language. So that regular languages are closed under intersection. Third closure property of regular language is concatenation. So taking an example, first is suppose to L1 belongs to the language AB, BAB, L2, BB and BA. So third one, concatenate them L1 dot L2. To see the result of L1 dot L2 is A double B, A double B A, BA triple B and BA BB A. So see the result of L1 dot L2 also belongs to a regular set or regular languages. So we conclude that in case of concatenation, regular languages are closed under it. The fourth property is complementation. So L1 A plus B whole star. Then L complements of L is nothing, that is 5. Now L equal to 5, then the complement of 5 is A plus B whole star. So again we conclude that in complementation, regular languages are closed under it. So the final overall, it's conclude that this particular diagram, the four properties, or we define the DFA, NFA, the closure properties of DFA, NFA, how to perform computation in case of DFA and NFA. So that particular Chomsky classification we define under the circle. There are regular expression. First is the regular expression, the smallest power O to the power 3 or O to the power n mod 3. It is the regular language. Context free language A to the power n, B to the power n. Again see the example of, and its acceptance model is push down automata. Context sensitive language, that is type 1 language. To see the example of type 1 language and its acceptance model, linear bounded automata, A to the power n, B to the power n, C to the power n belong n greater than equals to 0. In case of algorithm, it is decidable algorithm. And according to Chomsky classification, type 2 another divided into computational enumerable or non-computably enumerable, that is the halting problem and non-halting problem. So we conclude that a particular lecture, in overall lecture we learn about the DFA and NFA, the first property of Chomsky classification, type 3 grammar, the complete comparison between DFA and NFA. To make the DFA and NFA property, we cover all the tuples and how to perform in a particular regular expression. If language is given, then we find out the deterministic finite automata. Again, the language set is given to perform a non-deterministic finite automata, and the regular expression to finite automata. Okay, thank you everyone. Thank you.